Hi, my name is Silvy. I will be going through our paper Deep Learning in the Wild for Industrial Scale Plastic Waste Sorting, which has been accepted to the third Muslims in ML workshop. This project is funded by the US Department of Energy and developed in collaboration with Purdue Fort Wayne and UHV. Let's start by an overview of current plastic waste problem. As the world relies more on plastics, large amounts end up in oceans and landfills. Low-density polymers break down into microplastics. These microplastics spread through wind and causes serious environmental pollution. On plants, it impacts their growth, development, and photosynthesis. In aquatic life, it builds up in the hearts, intestines, and gills. Additionally, cardiovascular diseases in human animals are directly connected to microplastics. Wealthy countries dealt with their plastic by exporting it to China. After China's sword policy, these countries shipped their plastics illegally until 2022. The graph in the right corner shows the change in plastic waste exports to non-OECD countries over time. To top it all off, the widespread use of plastics has fueled remarkable economic growth in the global market. Currently, material recycling facilities rely on a combination of manual, semi-automated, and fully automated sorting systems. These systems utilizes manual labor, NIR, XRF, and vision-based technologies. However, semi-automated sorting remains the most prevalent. Challenges such as the low market value of plastics other than PET and HDPE, health risks to human labor, and issues with contaminated or dark plastics persist. MRFs report that 35% of colored plastics are incorrectly sorted and 5% of sorted bales are rejected due to contamination. As our project is to recover municipal solid waste, we focus on current viable datasets on MSW. But unfortunately, at the time, we only found 3 datasets which offer exceptionally low number of samples for the scale of this problem. On the other hand, recent approaches to the plastic sorting have evolved from traditional spectral-based methods to sophisticated ML solutions. But these approaches still lack real-world deployment. Our dataset stands as the most comprehensive collection of plastic found in municipal solid waste to date. The materials were sourced from the Solid Waste Authority in Florida. While our initial collection included 10 material categories, including all plastic types, aluminum cans, paper, and mixed plastics, this project focuses specifically on 5 types of plastics. The data collection process was semi-automated. Initially, we sorted the first few bales by hand and consulted with plastic experts for evaluation. Once trained, the EcoSorter took over the data collection process, improving its performance through iterative training over time. Ambiguous cases such as scratched or contaminated plastics were sent to the NIR facility at INL for precise identification. Finally, we curated 3 variations of this dataset. The EcoSorter stands out due to its integrated pipeline, which simultaneously classifies and collects data. After collection, the data is utilized for further classifier training. The pipeline is designed to be scalable and modular, allowing for easy adjustments as needed. We trained classifiers on all dataset variations and selected the normal dataset for deployment. To ensure robust classification, we implemented target data augmentation for underrepresented classes. Given the constraints of the EcoSorter, which is equipped with an 1080 Ti GPU, we needed to ensure that our models were both compatible with the hardware and capable of real-time performance. After extensive training and fine-tuning of 4 different architectures on our dataset, we developed a modified ResNet 50 which achieves an accuracy of 87.19% in 0.181 millisecond. To address the challenges of dark plastics, we utilized Yellow V5 for finer segmentation, ensuring that materials are accurately prepared for the classifier based on their training data. Yellow V5 was specifically employed for segmentation due to the complexity of the classification task and the need to optimize inference time. One of the key challenges in plastic sorting is addressing the impact of deformations. Deformations alter the visual and spectral features of plastics, although their fundamental characteristics remain unchanged. Our experiments on plastic deformation aim to understand how the model performs under these conditions. By incorporating more data and introducing more variability, we evaluate the model's ability to improve. We trained 3 models using 50%, 75%, and 100% of type 7 objects, which primarily consist of Arizona teach ducks. This approach provides insights into how the model handles both pristine and deformed materials. The model trained on 50% of the dataset resulted in only 51% accuracy on unseen data. Expanding the dataset to 75% improved accuracy significantly to 89.93%, while using the full dataset further increased accuracy to 93.75%. This demonstrates a misclassification reduction of 11.4% from 50 to 75% dataset size, compared to only a 0.99% improvement from 75% to 100% dataset. In conclusion, the diminishing returns observed between 75% and 100% dataset utilization highlights that the marginal gains do not justify the additional time, energy, and financial cost of further data expansion. t-SNE and Grad-CAM was utilized to have explainability of the models employed in EcoSorter. t-SNE helped us understand what our dataset lacked and what could be improved. On the other hand, Grad-CAM gave us critical information on misclassified objects. With more explainability, EcoSorter's pipeline ensures it is ready for industrial cases. Finally, our proposed sorting system demonstrates commercial viability by processing 200 samples per hour with a potential cost of $30 per ton. It requires minimal labor and ensures 5 types of plastics are sorted and data collected. This work establishes a foundation for future improvements through synthetic data generation for underrepresented plastic types and continuous learning mechanism for dynamic adaptation to new materials and deformation. Thank you.